Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 68. It's on acid-base equilibrium. At Harvard University, they have this wonderful Chinese statue that was donated on their 300th anniversary, and it has this inscription that talks about the importance of knowledge to civilization. Sadly, during the winter, they have to cover it up, and that's due to acid rain. Seems like a confusing solution. And acid-base chemistry is sometimes confusing to students and teachers, but you just have to understand that it's a reversible reaction. What does that mean? It'll eventually achieve equilibrium. And we've learned that you can measure the equilibrium constant, and that gives us a better understanding of really what's going on in acid-base chemistry. Remember that equilibrium constant is simply the products, or the concentration of the products, divided by the concentration of the reactants. Now, what is an acid or a base? Remember, it all relates to proton exchange. And so if you're donating a proton, you're going to be an acid, and if you donate or you accept a proton, then you're going to be a base. And so we can measure the equilibrium constants of acids and bases and determine if they're strong, in other words, they're favoring the products, or if they're weak. We can also combine acids together, and we have what's called a neutralization reaction, and we can measure those using titration and titration curves. And so the first thing that you should understand is the importance of water. All acid-base chemistry takes place in the presence of water, and so we can think of an infinite amount of water surrounding every acid or base. It's something that we can simply ignore. There's always going to be water present. Water is also important because it is amphoteric, and what that means is it can serve as both an acid or a proton donor, or a base, a proton acceptor. And so if we were to look at a simple reaction, here we have acetic acid and water, what's going to happen is that the acetic acid is going to be the acid and the water is going to serve as the base. It's going to accept protons from acetic acid. Now, as it does that, it's essentially forming an acid, and since this is a reversible reaction, it can push back towards the base. And so we have these two pairs. We have these acid-base pairs. And to keep it straight, we'll call everything on the left side an acid and a base, and every on the right side a conjugate acid or a conjugate base. If we were to look at another reaction, in this case we've got ammonia. Ammonia is going to serve as the base, and so the water, since it's amphoteric, in this case is actually donating a proton, and it's forming that ammonium ion, which is the conjugate acid, and then we have the hydroxide, which is going to be the conjugate base. What's cool about water is it can autoionize. That means it can serve as both an acid and a base. And so what we're doing is essentially donating a proton to another water molecule. And so if we look at that, what we're forming is something called hydronium, and then the one that loses the proton is going to be a hydroxide. And we can measure the K value of this. We can measure the equilibrium constant of that. And it ends up being 1 times 10 to the negative 14th, which is going to be a really, really small value. Now, what is equilibrium constant? Remember, it's going to be the concentration of the two products divided by the concentration of the two reactants. Why do we have a 2 here? Remember, it's because we're going to have 2 moles of water on the left side. Now, as I said earlier, there's always water present, and so in this equilibrium constant of water, we can essentially ignore water. And so this is going to be our Kw value. Since it's 1 times 10 to the negative 14th, then we can just figure out that the concentration of hydronium and hydroxide, therefore, must be 1 times 10 to the negative 7th. Therefore, pH, which is the negative log of the hydronium, is 7. It's easier to deal with it that way than these really, really ridiculously small numbers. Likewise, pOH is going to be 7 as well. So if we add pH and pOH, it'll always add up to 14. Now, what's the difference between a strong or a weak acid or a base? Well, the equilibrium constant is going to help there as well. So if we look at acetic acid, in this case, it's donating a proton to water, and so we can figure out its acid ionization constant, which is essentially an equilibrium constant. So if we were to write it out, it's going to be the concentration of the two products divided by the concentration of only one of the reactants, Y. Again, we're simply ignoring water. If we were to measure that, we find it's a ridiculously small number. What does that mean? Since the equilibrium constant is so small, it's actually favoring the reactants. That means most of it is not actually donating its proton. And we call something like that a weak acid. If the Ka value is ever less than 1, in other words, it's favoring the reactants, then we're going to call that a weak acid. And carboxylic acids are notorious for being weak acids. Those are acids that have this carboxyl group in it. Now, sometimes it's hard to measure Ka or deal with those numbers, and so you'll see pKa, which is simply the negative log of Ka. If we were to look at a strong acid now, this is hydrochloric acid combining with water, and figure out its Ka value, it's an incredibly large number. What does that mean? If we have a hydrochloric acid, it's essentially all donating its protons. It's all shifting towards the right. And so if our Ka value is ever greater than 1, that means we've got ourselves a strong acid. And there are simply 6 strong acids that in AP chemistry you should memorize. Hydrochloric acid, sulfuric acid, simply memorize those. And there's a cool YouTube video that shows you how to do that. We also have what are called polyprotic acid. What are those going to be? Those are going to be acids that actually have 2 protons, and so they're going to donate that proton in 2 steps. Now, if we were to look at the general equation then for an acid, it's donating a proton and forming hydronium. We could write it like this. And if we were to look at the general equation for a base, it would look like this. And so we could also use the equilibrium constant of the base. If it's ever going to be less than 1, what does that mean? It's actually favoring the reactants, and it's going to be a weak base. There are 4 groups of those. And if it's ever greater than 1, then it's favoring the products, and these are going to be all of the strong bases that we have. You can see that they're all going to be hydroxides formed by combining with atoms from group 1 and group 2. And so what's a neutralization reaction? That's when we're getting a reaction between an acid and a base. And there are really 3 groups that we could have. We could have a strong acid and a strong base. And what happens there? They all are forming water. We could have a weak acid and a strong base. What's going on there? Well, basically we're going to take that conjugate acid and it's going to form a conjugate base. But remember, it doesn't form all of that right away. And then likewise with a strong acid and a weak base, we're going to have that weak base forming a conjugate acid, and so it's not going to all transfer those protons. And so we can use acid-base titrations to look at that. So what would it look like if we're doing a strong acid and a strong base? Well, let's set this up with a burette. What we're going to do is be adding sodium hydroxide to hydrochloric acid. You can see down here in the Erlenmeyer flask that we have a pH that must be less than 7. We're using phenolphthalein as an indicator. And so if we add some of that sodium hydroxide, eventually it turns pink. So that tells us that at some point it went towards a greater than 7 value. If we were to actually graph the pH over time, it would look something like this when we add a strong base to a strong acid. And so what's going on here? Well, at this point, we're adding a lot of this base. It's converting that acid into water, but the pH isn't changing very much because we have lots of this strong acid still in the container down at the bottom. Eventually what happens is we reach equilibrium or the equivalence point, and then all that base that we're adding is simply going to pump it up towards a more positive pH value. It's going to become basic. And so we have the smooth curve. We simply split the difference. When we're adding a strong base to a strong acid, that equivalence point is going to be right at 7. Now, what happens if we add a strong base to a weak acid? And so in this case, we're going to have acetic acid in the bottom, and then we're going to add a strong base, so that's sodium hydroxide. And you might think, since we're adding this strong base, it's simply going to turn quickly like that. We're going to add the base, it's quickly going to get rid of all of that conjugate acid, but if we were to do the titration, we get a curve that looks more like this. And so what's going on is it starts to increase like that, but eventually what we're doing is we're creating a bunch of this conjugate base, this acetate ion over here. And so this whole period of time right in here, what we've essentially created is a buffer solution. And we'll talk more about that in the next video, but what it's going to do is it's going to stabilize the pH. It's not going to change very much. And then eventually what happens is it's going to go towards the base. We're going to reach an equivalence point, but look at the equivalence point right here. That equivalence point is going to be much greater than 7. So it looks like it's somewhere about 8.2 in this case. Now what's causing that buffer solution, remember, is Le Chatelier's principle. What we're doing is we're adding more of the base, which is forcing more of that acid to be converted into a conjugate base, which is stabilizing that pH. Likewise, if we were to look at a strong acid and a weak base, so we're starting at a really high pH right here. As we add the acid, it starts to drop down really quickly, but now we've created a buffer solution right here, and the equivalence point is going to be lower than 7 in this case. So you should understand what those titration curves look like in each of those 3 different situations. And so did you learn the difference between a strong and weak acid and base? Remember, that's based on the equilibrium constant. Did you learn how strong and weak acids behave in these titration reactions? Did you learn that neutrality, in other words, a pH of 7, requires the concentration of the hydronium and the hydroxide ions to be equal. And then did you understand in each of those three situations what happens during a titration? I hope so, and I hope that was helpful.